Okay, thank you. I'm taking this chance to introduce my recent study, a hybrid analog ensemble convolutional neural network method for post-processing precipitation forecast. I'm Inkai Sa from Water Forecast Research Team at University of British Columbia. Collaborators of the work are David Garnier from National Center for Atmospheric Research, Dr. Gregory West from BISA Hydro, and Professor Roland Stahl from UBC. In the study, we aim to post-process ensemble precipitation forecasts, producing bias-corrected, calibrated, and physically realistic spatial temporal sequences. We wish our study can add values to hydrological applications, such as the management of hydroelectric facilities. Here we're working with the Global Ensemble Forecast System, GEFS. Our target variable is quarter degree total precipitation, and we're focusing on its 0 UTC daily initializations straight hourly forecast from day 0 to the end of day 6. Region of interest of the study is British Columbia, and forecasts here are verified against BISA Hydro station observations. Locations of the stations are shown in the map with elevation backgrounds. We have clustered our stations into 3 groups, and they are the South Coast, Southern Interior, and the Northeast. The overall method of our study is analog-ensemble convolutional neural network hybrid. This method relies on 3 post-processing models in sequential order, and they are the analog ensembles, minimum divergence, Schaake shuffle, and a convolutional neural network. A bit more about the technical details. So the first 2 statistical models are trained with 15 years of data. Their training inputs is GEFS reforecast, which is produced by the same configuration as the operational GEFS. And then the training target is the European Center for Medium Range Water Forecaster Analysis version 5 or the year A5. Our convolutional neural network has been trained with 2 years of data. It takes the output of previous method as input. Here we provide details of our 3 post-processing models, and here analog ensembles. So we use this method to identify the univariate relationships between GEFS ensemble mean and our ERE5 training targets, and it is achieved through a nearest neighbor search. Then in the inference stage, when today's forecast becomes available, the same relationship will be memorialized and applied and will already produce 25 analog ensemble members. In addition, a data augmentation technique known as supplemental location, SL, is applied to increase the number of training samples. So visually the circles in the graph. We now move on to the second one, minimum divergence Schaake shuffle. We use this model to reconstruct the spatial temporal consistencies of our analog ensemble members. This is a necessary step because analog ensemble members are equally likely on individual locations and forecast lead times. So we don't know how to connect them to represent the evolution of forecasted precipitation events. And then Schaake shuffle is a method that can solve this problem. It obtains analyzed precipitation sequences from the past. It extracts their rank structures as training targets, which is also known as dependence templates. And then in the inference stage, the same templates are memorialized and applied to analog ensemble members, and it produces spatial temporal sequences. Now back to the minimum divergence part. So this is a feature engineering strategy, which means we objectively selecting analyzed sequences by minimizing their distribution divergence against our analog ensemble members on each initialization time. Our last model is a convolutional neural network. We use it because we found that the output of the previous 2 models typically contain a higher amount of noise. This negatively impacts forecast skills, and is also disastrous for all applications, such as downscaling. And here we take previous method output as inputs together with precipitation multi-climatology and graded elevation as additional predictors. We train a convolutional neural network to reduce the impact of noise, and it produces more skillful forecasts as the final output of our method. Here, in order to prove our convolutional neural network idea and our post-processing method overall, we have conducted experiments in the past 3 years, and it is based on members of 2 groups. And the first group is the control parts, which rely on statistical models only. And then the second group is ours, which combines a pair of statistical models and a convolutional neural network. So then by contrasting the output of these 2 groups, we can estimate the actual benefit of having an additional CNN in our post-processing pipeline. And also the control members are ended with H15. This is because they are rooted from existing research that apply the same analog-ensemble method in the continental US. So they are state-of-the-art and they are competitive enough to participate in our post-processing experiment. Here we provide some example outputs to illustrate the whole idea. So the top left panel here is an example of analog ensemble member, and the top right panel is corresponded ERA5 training targets. And so if we compare these 2 panels, we can see that the analog ensemble member has the ability to produce precipitation values along the coast and in the interior parts of the domain. And actually, for individual grid points, their forecast errors have been reduced. However, together, these grid points failed on delivering pattern-based information. And our solution to this is minimum divergence Schaake shuffle. Here, if you look at this example I put on the bottom left, we can see a big improvement. And the only suboptimal part here is the small scale noise. A good way to visualize it is drawing contours in the interior parts of the domain, where we can see inconsistencies between the windward side of Canadian Rockies and the rain shadow zone in the middle. We fully applied CNN to solve the small scale noise problem, and this example output is on the bottom right. And here we can see that precipitation patterns are organized better, and the noisiness or inconsistencies is mostly resolved. So this is expected to be the final output of our method. Here we move on to systematic verifications. And here we'll provide results in the rain season of October to March during the verification periods. The top 2 panels are station-wise mean continuous ranked probability skill scores. Higher means better, and they are functions of forecast lead times from day 0 to day 6. Here we provide 2 verification highlights. So first one, you see that all the lines decrease with increasing lead times, no surprise, but they're all at least larger than 0, which means they're better than climatology reference. As in point 2, we see that different lines have different skill score difference, and the bottom 2 panels computed this actual difference between ours ending with the CNN and the H15 controls. So we can see consistent performance gains in all forecast lead times, and they are statistically significant. We also provide verifications of 7-day accumulated heavy precipitation. And our definition of this event is the 90th percentile of precipitation monthly climatology. Here the results computed within the southern interior stations, because precipitation in our region of interest is not equally distributed throughout the domain. And recalling our station location plots, this covers Canadian Rockies and some lee side of coastal mountains. Here results are visualized as reliability diagram. So its x-axis represent forecast probability, and y-axis represent observed relative frequency. Diagonal reference line in gray color is the perfect reliable line, and the red color line here means bar score equals to 0, skill score equals to 0. And the bottom panel is the frequency of usage, so it visualizes how frequent each forecast probability is issued. Here we also provide two verification highlights. So first one, we see that all the members are generally reliable by staying around the gray line. They're slightly less confident for heavy precipitation, like high probability forecast, but none of them fall to the no skill line level. So given that our post-processing was conducted on individual lead times, and here their 7-day accumulated quantity can stay reliable overall, we think it is evidence that they actually represent the evolution of precipitation events. And that's why their temporally accumulated quantity can be reliable. And our second verification highlights is about the decomposition of wire scores. And here REL means reliability and RES is resolution components. So here you can see that ours ending with CNN are more reliable because it's lower, and we also provide better resolution because it's higher. So higher resolution is a highly preferred quantity because it means ours will less likely respond in climatology mean and will be more active on detecting region shifts for the incoming heavy precipitation events or sequences. In addition, we have done more verifications, for example, in other station groups and different heavy precipitation standards, and our conclusions are all roughly the same. So here we move on. So in the study, the analog-ensemble convolutional-neural-network hybrids is proposed to bias correct and calibrate the GFS precipitation ensembles. And this method uniquely combines three post-processing models, which are the analog ensemble, minimum divergence, Schaake shuffle, and a neural network. We have conducted post-processing experiments for 3 years, and during the experiment, ours produced more skillful forecasts by showing higher CRP skill scores. We've also verified 7-day accumulated heavy precipitation, and ours also produced more skillful calibrations in this verification case. Currently, we've taken actions on a research to operation transition. So in the near future, we're looking forward to results from a near real-time system of this research. And finally, a border vision. So this research is based on GFS and in British Columbia. So future research can consider similar post-processing paradigms in other areas and with other forecast products. That's the end of presentation. So just in addition, we have submitted our study end of November last year, and we've started releasing our source codes on GitHub. So feel free to email me or post GitHub issues for feedback. And with that, I'm happy to take questions. Thank you so much.
Great, thanks for your talk. And we have about, I guess, 30 seconds or so. Are there any questions? I didn't see anything in the chat at this time. But
I have a comment at least. I use that package very often, and it is very nice. So thank you for making it.
Thank you so much for being the user. Yeah, let me know if you have any suggestions and so on.